Hey everyone, let's continue our study of quotient groups and homomorphisms and the connection between the two. So here's just a reminder of something we learned about earlier. So recall, if little g is in capital G, then the mapping, I don't remember what symbol I used, probably, no, let's just call it phi sub g, I'm pretty sure I used phi sub g, from G to G, defined by phi sub g of x equals gx g inverse. Remember, this process is called conjugation. And so this function right here, defined in such way, is actually an automorphism of G, right? So that means that it is an isomorphism from G to G, and it's called an inner automorphism. So there, for a given group, there might be a whole bunch of automorphisms of G. Not all of them arise in this way. So this is a special type of automorphism. It certainly does not cover all possible automorphisms of a given group. Now, you can check so let's say it like this. So if we let in of G equal the set of all inner automorphisms, so phi sub G, where little g runs through all of capital G. So you can check if we use this notation right here, then in G is a subgroup of aught G. Right, so it's not necessarily the entire collection of automorphisms, but it is a subgroup. And then here's the first thing that we want to, the first theorem we're going to have. So this is theorem 15.4. If we have any group, so if G is any group, then G mod the center, right, that's Z of G. Remember, the center is the set of all elements in capital G that commute with everybody. So then this quotient right here, we know that Z, the center, is a normal subgroup. G mod ZG is isomorphic to the group of inner automorphisms of G. So that's kind of a funny looking result, but it turns out to be true. Right? This quotient right here is isomorphic to the group of inner automorphisms of G. And to prove this, we're going to use the first isomorphism theorem. So for the proof, let's see now. If I want to use the first isomorphism theorem, what I want to do is come up with a homomorphism that goes from G onto in G, such that the kernel is equal to the center. So let's define F from G to in of G in, I don't know, sort of the obvious way. So define this by, so little f, or f of little g. So which inner automorphism would you want to associate little g with? The obvious choice would be phi sub g. Now, let's do some of the details, and we'll leave some of the details for you. But the point is, we would like to show that this is an onto homomorphism. Then we identify the kernel. If we can show that the kernel is equal to Z of G, then the first isomorphism theorem does the work for us. Given let's call them little g and little h. So little g and little h in capital G, note that, and I guess I need a little x in there. Well, it's fine. Okay, note that F, let's do it like this. Note that phi sub gh of some little element x, that's going to equal gh times x times gh inverse, which is equal to gh times x times h inverse g inverse. And now I'm going to move some parentheses around, so this is going to give me a g times h x h inverse times g inverse. And this is equal to, so what's this? Keep going with this equality here. This is going to be, so let's see, inside, that's phi sub h of x. And then we have phi sub g applied to that. So that's going to be phi sub g of phi sub h of x. Thus, so what did we show? We showed that f of gh, that's this, is equal to f of g times f of h, where we remember that times in this setting means composition of functions, which is what we have right there. And so, f is a homomorphism. And I'll let you do the details here. So let's say check, and you definitely should do these details. So check that f is onto. I think that's fairly obvious, right? An element here is the form phi sub g, which means that there's a little g over here that gets sent to it. So that means it's onto. So check that f is onto, and that the kernel of f is exactly equal to z of g, right? So that's a nice little exercise for you to do. Okay, so that completes the proof, and so we now know that the quotient is exactly isomorphic, or the quotient g mod z of g is exactly isomorphic to the group of inner automorphisms of g. And now I want to see this in example. So let's do that here. So in, where do I want to work? I want to work in D6. Let's let rho, yeah, let's call it rho. So let's let rho be 60-degree rotation counterclockwise. Right, so that's one of the typical elements. Remember, D6 is the symmetries of a hexagon, and so rho would be, right, the rotation that moves the dial one click, right, one click to the left, if you like, right, counterclockwise. Now you can check. So it turns out that the center of D6, so Z of D6, well, it definitely has the identity, and it also has rho cubed, right? So that would be the 180-degree rotation. It turns out that that's the entire segment. So since the order of D6 is equal to 12, we have that D6 mod the center of D6 has order 6. Okay, now there are exactly 2 groups of order 6. All right, every group of order 6, it turns out, is isomorphic to one of 2 possibilities. So we can say it turns out that the group of inner automorphisms of D6 is isomorphic to Z6, that's one of them, or S3, right? Those are the 2 groups of order 6. Every group is isomorphic to one of those 2. And since we know that this group right here, this quotient, is isomorphic to the group of inner automorphisms, we know that in D6 has to have order 6. A group of order 6 is one of those 2. Now, if in D6 is isomorphic to Z6, then G mod ZG is cyclic, and remember the theorem we had before, right? This will be cyclic if and only if, well, or no, I shouldn't say if and only if it's cyclic, then G is abelian. What was the theorem number? Where did it go? Yeah, sorry, 15.3. So by, oh shoot, I'm sorry. I wrote this badly. Then, sorry, let me fix this. So if this is isomorphic to Z6, then D6 mod Z D6 is cyclic. So then by theorem 15.3, we conclude that D6 is abelian, which we know is not true, right? D6 is a non-abelian group, and so that means that it's not Z6, right? Right. So we conclude which is false. Okay, so that rules out that possibility, which means that in D6 has to be isomorphic to S3. All right, so therefore, in D6 is isomorphic to S3. So there's a nice application where we applied our a couple of previous theorems, right? And that allowed us to get a handle on the isomorphism type of the inner automorphisms of D6. I'm going to prove another result now. Let's clear some space. And so this is another example of making use of the quotient to get some information about the original group. And so this is going to be called lemma 15.5. And it's a lemma because we're actually going to use it in a big theorem next. So let's let G be finite. And we need a normal subgroup, so let's say N is a normal subgroup of G. And then it goes like this. If G mod n, right, has an element of order k, then G has an element of order k. So, as I was saying, this is an example making use of some knowledge about the quotient to get some knowledge about the original group. So for the proof, let's take our element of order k in the quotient. So let's let Gn in G mod n have order k, and by the way, we can assume that it's greater than or equal to 2, right? Of course, G has an element of order 1, the identities, right? So there's nothing interesting there. So let's take a coset in the quotient group, right? An element of the quotient group, right, that has order k greater than or equal to 2. So then, what does that mean? It means, well, let's see, what does that mean? It means that little g raised to the k lives inside capital N. Right? So let me write that out. So then we know that n is equal to g to the n raised to the k. All right, if it has order k, that means that when you raise it to that power, you get the identity. The identity is the coset n. Now, to do the computation here, what does Gn raised to the k mean? It means little g raised to the k times capital N. And now, what does it mean for these two cosets to be equal? It means that g to the k has to live inside n. So we can say, and so, g to the k equals little n for some little n in capital N. It also means, and this is the order part, so in addition, so because k is the order, that means that Gn raised to any smaller power is not equal to capital N, which means that g raised to any power less than k cannot be inside n. So we can say, and in addition, g, what symbol that I use here, g raised to the jth power, so g to the j is not an element of n for 1 less than or equal to j, strictly less than k. Okay, so now remember what we're trying to do. We're trying to produce an element living in G, capital G, right, that has order k. Right now, what we have is a coset that has order k. And then we also have this property that g raised to the kth power lives inside capital N. Okay, so now, let's see how I want to say this. So G is a finite group. And in which case, and that means that every element has finite order. In particular, little n has finite order. So since capital G is finite, n to the p is equal to the identity for some integer p. I guess I should say for some natural number. Yeah. For some natural number p. So now what does that mean? So now we have, let's see, so n is equal to g to the k. So g to the p, yeah, say it like that, g to the p raised to the k is equal to g to the k raised to the p. Nothing exciting going on right there, but this is equal to, let's see, g to the k is equal to n, so this is n to the p, and then we know that's the identity. All right, so now that does not tell us that we found an element of order k, but we do have g to the p raised to the k is equal to the identity. So at least now we know that the order of g to the p is less than or equal to k. So it follows that the order of g to the p is less than or equal to k. So now, what we want to do then is actually show that g to the p does have order k. And so we're going to say, all right, what if g to the p raised to some smaller number, let's say little I, is equal to the identity? So suppose g to the p raised to the I is equal to the identity for some I strictly less than k. Well, so then, then what? Then n, which of course is equal to e times n, is equal to g to the p to the I times n. And so g to the pi is an element of capital N. So what does that mean then? So let's see. The order of g to the n has to divide this number right here, p times I. So it follows that k divides p times I. Let me make sure that's what I want to say. Yep. And so pi is equal to a times k for some little a. Some natural number here. Now, since k, let's see, how does k relate to I? K is greater than I, so since k is greater than I, and notice what we have here, so k is greater than I, which means that p has to be greater than a. Is that what I want? Yep. So since k, we see that, what did I just say? So k is greater than I. To balance this out, we would need p greater than a. So we see that p is greater than a. So now, equals, which is G, wait, what? G equal to the PI, right? To the PI equals G to the KA, which is equal to G to the I. Sorry, G to the K. Oh, that's a mistake in my notes there. Oh, no, that's a K. G to the K raised to the A. And so what do we have now? G to the K raised to some power smaller than P. In fact, let's write this out. That's N to the A, right? G to the K is equal to N. So this is N to the A. And so now what we have is some number A smaller than the order of N is giving us the identity as an exponent, right? That contradicts. So let's say that this way. So this contradicts the fact that the order of N equals P, right? What do we have? We have an exponent smaller than P that gives us the identity. All right, so therefore, no such I exists, right? So therefore, the order of G to the P is equal to K, right? So that gives us an element of capital G that has order K, right? Namely, little g to the P. Just check the time here. Let me see what I need to do next. Yeah, I think that's a good place to stop right here, and then we'll pick up with our next results. So this lemma is going to be used in the proof of our next result, and we'll do that next time because it's kind of a complicated proof coming up. So, all right, we'll see you then.